Hi, my name is Madeleine Udell. It's a pleasure to be here with you today. I'm going to tell you about how to automate machine learning and why you might want to do that. I'm a professor of operations research and information engineering at Cornell University. And I want to tell you that a lot of this presentation is joint work with my student, Chengrun Yang, who is a PhD student here at Cornell. So first I want to tell you why we would want to automate machine learning. What's wrong with just doing it yourself? So it starts with the fact that there are so many different machine learning problems. They're becoming more and more common across more and more domains. Different people in different domains are finding new data sets, and they want to predict something using this new data set. Okay. So all this is well and good. And in fact, we've got lots of different and interesting machine learning methods that they could use to solve these prediction problems. If you take a look at the models in scikit-learn, you'll find a lot of great ones, right? Like maybe we could try a k-nearest neighbors classifier, maybe a Gaussian process classifier. What about a decision tree? What about a random forest? Maybe we should use, quadratic discriminant analysis, right? There's so many different methods you could try. There are linear methods, there are nonlinear methods, there are tree-based methods, there are neural net-based methods, right? So many. How do you decide which one to use? Well, unfortunately, trying them all takes a long time, especially when you start thinking about the fact that each algorithm has its own hyperparameters, and the performance of the method also depends on those hyperparameters. You can imagine just trying everything. It takes a really long time. We don't just want to, pick one just randomly, because different algorithms actually perform differently. Different models perform very differently on the same data set. This is an example that's sort of classic, that is sort of right up there on the landing page for scikit-learn. And they'll show you three different interesting data sets. Okay, so this first data set, this is called the 2 moons data set. You can see there's like a moon-like shape of red points and a moon-like shape of blue points. Okay, and on this data set, you can see the performance of all sorts of machine learning models. And some are able to fit the 2 moons pretty well. So I think a lot of these ones in the middle are fitting the 2 moons pretty well, but you can see that the way that they generalize is actually quite different, right? The way that they would sort of extrapolate to points up in this upper right corner or down here, they're going to be quite different. And then there's some models that just fit this data set very poorly. Like for example, the linear SVM does a very bad job on 2 moons. You can also see the neural net actually does very poorly on two moons. Okay. Then you can look at other data sets, right, with other structures, right? This one has an inner ring of blue and an outer ring of red. You can see, again, the linear model does pretty poorly. And then a lot of these other models do decently well. You can see that some of them are sort of more naturally find circles, others more naturally find squares, and it's a little bit of a weirder fit to this, concentric circles data set. And then the last one is actually fit quite well by the linear model. And all these other ones are finding some sort of weird blobs. Maybe they're overfitting, maybe they're not. Hard to say, okay? But we've got lots of different models that perform differently on these different data sets. And when here it's actually pretty easy to tell which ones are going to perform well, because this is a 2-dimensional data set. But if you imagine a data set where you've got lots and lots and lots and lots of input features, you can't visualize what's going on quite as well as you can here. And it can be hard to pick what kind of model is going to do the best on your data set. So more generally, right, we've got a lot of decisions to make when deciding what kind of model to use to fit your data set. Okay, so you start with your raw data set. And what's the first thing you might do? Well, you might look and see if there are any missing entries in your data set. If so, maybe you'd impute them by, say, the column mean, or maybe you'd impute them by zeros, or maybe you do, some fancier imputation method. Maybe you have some categorical data or some ordinal data. And that you might encode as binary numbers using, say, a 1-hot encoder. The next step might be to deal with the real valued features. It's pretty common to standardize or whiten your data, but maybe you don't want to do that. Maybe that actually hurts the performance on your problem. And maybe there's some other way of standardizing your data that you think would work better, like pre-processing with like a Gaussian copula model. Okay. The next step might be reducing the dimensionality or feature selection more generally. Right? Maybe they're only as a subset of the features that you really need to use for your model. Or maybe you can reduce the dimensionality using, say, PCA. And the last step would be to choose an estimator to fit your model. So for example, here in this example pipeline, I'm showing an estimator of k nearest neighbors using k equals 5. So using the 5 closest points in order to form your prediction. Okay, so this is a lot of choices to make, right? And then each of these choices, right, each of these components has its own hyperparameter, right? So the estimator, we need to choose the number of neighbors in the nearest neighbor. Even if we've decided to reduce dimensionality with PCA, we need to know what, how much to reduce the dimension. So there's lots of choices to make, and iterating through all of these could take a really long time. Okay. What's worse is that, I mean, you really want to make these choices, right? You don't want to just say, I have found the one best true pipeline, and I will use it for everything in the future. Okay, so we actually did this test on a collection of 215 mid-sized data sets from the OpenML collection of data sets. We went through all the data sets, we tried a whole bunch of pipelines on all of the data sets, and we found the pipeline that performed best on average. Okay, and what did that look like? It imputed the missing entries by the mode of the column. It encoded categoricals as integers. It standardized the data. It removed features with 0 variance from the data set. And the final estimator that we found was the best on average across all data sets was gradient boosting with a learning rate of 0.25 and a maximum depth of 3. Okay. So that's what we use to make our predictions, right? That's the best on average pipeline. Now, is that the best pipeline? No. On most data sets, that is not the best pipeline, okay? In fact, even if you just look at the estimator component for each data set, and when you look at the best estimator for each data set one by one, you'll find that for almost 40% of the data sets, the best estimator is gradient boosting. So that is a pretty strong machine learning method. But other methods are sometimes better, okay? So for some data sets, you want a multi-layer perceptron. For some, you want k-nearest neighbors. For some, you want AdaBoost. For some, you want extra trees or logistic regression or decision trees or random forests, okay? So if you want to do the best on each data set, you do need to consider these all the possibilities, okay? It's also interesting to think, are there some characteristics of the data set that you could use in order to predict which of these methods is going to work best? Right? Could you meta-learn which machine learning model will work best on your data set? Okay. In fact, this has been immortalized into a theorem by Wolpert in 1996 that there's no one model that works best for all problems. This is sometimes called the no free lunch theorem. Okay, on the other hand, automated machine learning is trying to help you solve your problem. So it's not going to solve it in a theoretical sense, but it is going to solve it in a practical sense. Because instead of iterating yourself through all of these different machine learning models and trying out all these pipelines, you can call an automated machine learning method that will in some sense do it for you. Okay. So I'm showing you examples of the APIs of a whole bunch of different automated machine learning methods. Okay, this one is AutoSKLearn. This is one called Flammel. This is AutoGluon. This is H2O. And I guess what's interesting here is just how short the code is. Okay, so once you have your training and test set, already imported, right? You can use H2O's AutoML in 2 lines. Flammel, in fact, even importing the package and fitting the data set. This is all 3 lines. Okay, so it's not very much code. This is an interesting trade-off, right? There's always a trade-off between programmer time and runtime or quality. But I would claim that for automated machine learning, sometimes you get better quality using less programmer time. Okay, so tweaking the hyperparameters yourself, probably not going to work as well as using one of these automated machine learning packages. Okay, so today I want to take you through some of the ideas that are powering these automated machine learning methods and to understand what's going on underneath the hood. Like, what are they doing in order to choose between all of these different pipelines and all of these different hyperparameters and give you back a really good machine learning model. So first, a couple of definitions. What is automated machine learning? Okay, automated machine learning is a method to choose a machine learning model and hyperparameters for you so you don't have to. And by machine learning model, that could mean an entire pipeline, or it could just be the estimator. There are a bunch of different kinds of automated machine learning depending on what parts of the pipeline they're really thinking about helping you with. So hyperparameter tuning is just choosing the best hyperparameters for the model. This might be something like the depth of a tree, or maybe the learning rate. Combined algorithm and hyperparameter search is sometimes called cache, that chooses an estimator together with hyperparameters. Neural architecture search chooses a deep learning architecture. So maybe it'll tell you the number of layers, what type of layers, the width of each layer, and the learning rate to use to train this model. This is, in general, a much harder problem because the cost of training of every evaluation is much higher. You might also think about how to initialize your model, and this is a major topic of interest. Then meta-learning is generalizing in a different direction. It's sometimes called learning to learn. It uses information from a large corpus of data sets in order to choose a better model for a new data set. So if your technique for building an automated machine learning system was meta-learning, you would first go out, collect a bunch of data sets that you think might be similar to data sets you'll see in the future. You would try out a bunch of different models on your collection of data sets, and then you would try to learn a mapping from the data set to which model works best on that data set. Once you have that mapping, then you can apply that mapping to new data sets in the future in order to predict which model will work best very quickly. I'll show you examples of all of these things. Automated machine learning methods are going to depend on what kind of data set you're looking at. And oftentimes you'll see different AutoML methods that are targeting different kinds of data sets. In this talk, I'm mostly going to be talking about methods that are geared towards tabular data sets. Okay, other kinds of data sets are also super interesting, but beyond the scope of this workshop. Okay, so let me tell you about the techniques that power these automated machine learning packages. Okay, maybe the first most basic idea is grid search. Okay, this is a really classical method where you say, I've got a bunch of different parameters in my machine learning model, and I don't know what the right value of the parameter is. So I'm going to define a sort of minimum value that I think might be useful, a maximum value that's useful, and I'm going to grid out the values in between those two. Okay, now I'm going to try each one of the values on that grid, and I'm going to see which performs the best. This is pretty standard. I bet a lot of you have done this. It doesn't work very well when you have a large number of parameters. Okay, and that's because the number of grid points that you would need to try grows exponentially. Okay, there's another really interesting idea that you can use to solve hyperparameter search problems in this setting that's also dead simple, maybe even simpler than grid search. And that's this. It's called random search. I'm going to take a minimum and maximum value for each parameter of interest, and I'm going to pick points randomly between the minimum and maximum value along each of these hyperparameter dimensions. Okay. When I do this, take a look at what happens with respect to each of these two dimensions. Okay. If I use a grid layout, then I'm only sampling 3 distinct values of each parameter. Okay, and so here I'm showing sort of this this thing on the side is showing which of the parameters, which value of the parameters I'm using, and this green curve is meant to say show the quality of each of those choices of parameters. So in fact, the highest quality point would be the top of this little green mountain. Okay, and what I'm showing is that the green parameter is very important, whereas the yellow parameter is not very important, right? This landscape is pretty flat, whereas this landscape is peaked. So because I've only chosen 3 distinct values of the important parameter, I miss the peak, okay? Whereas if I use a random search, you'll see that when I project these points to the important parameter, I actually am able to sample the peak of the mountain. I catch it, right? And actually, similarly for the unimportant parameter, I have so many more random points that'll actually find the peak of this. Now, if this is the real important parameter, then this is the point I'm going to take. So this is kind of interesting. Random search can work much better than grid search, right? This is maybe the first interesting idea in automated machine learning. Okay, Bayesian optimization is a completely different idea for how to optimize hyperparameters. Okay, the way that Bayesian optimization works is it creates a surrogate model for what the sort of the quality of your model as a function of this hyperparameter might look like. The most common choice is to say that the surrogate model is a Gaussian process. So it'll fit a Gaussian process model to the sort of the quality of the predictions you're getting as a function of this hyperparameter. Okay, so here's an example of Bayesian optimization. The points that you've evaluated are these black circles. So you've evaluated this value of the hyperparameter and it got you a pretty good model, and you evaluated this other value of the hyperparameter and it got you an even better model. Okay, now you try to fit a Gaussian process to the data that you found, so just to these 2 points, and the Gaussian process will tell you, I think maybe this is the most likely shape for that curve, and also this purple region, those are the error bars. Okay, so that's my, let's say, 90% confidence interval. Okay. Bayesian optimization then constructs an acquisition function. So it's trying to find the point that will maximize the upper envelope of this, say, 90% confidence interval. Okay, and so you can plot the 90%, the upper envelope of the 90% confidence interval, and you can look at the point that maximizes that upper envelope. Okay, so that's right here, and that's the point that I'm going to sample next. Okay, so now I sample that point. That's my new observation. So I actually evaluate my machine learning system at that new hyperparameter. That's my new observation. And I keep on going, right? I fit a new Gaussian process to the new observations I've made, continue. There's one thing that's kind of wasteful about all of these approaches is I've got all of these different methods that I'm, all of these different models I'm evaluating, and I might spend a lot of time evaluating a model that actually isn't very good, and where I could tell in advance that it's not very good. So instead of doing that, the idea of a multi-armed bandit approach is to budget the amount of time you're going to spend evaluating every pipeline. Okay, so first, let's sort of form a discrete set of all the pipelines that I might evaluate. So here, these are represented as slot machines, okay? And I'm gonna create a thing that I'm gonna budget, right? Maybe I'll budget training examples that I allocate to each of these machine learning models, or the training time, the time that I allow them to train, okay? I'm going to estimate the performance of each pipeline with a small budget, right? So you can imagine I'm gonna pull the lever on each slot machine once to start with, okay? And then I'll see which one looks the most promising, right? Maybe because I'm getting good value so far, or maybe because I haven't pulled it very many times, so I don't know that it's bad yet, okay? I'm going to take the most promising pipelines, I'm going to allocate more training examples to those pipelines, and continue. Okay, this works well with machine learning methods that can be trained sort of iteratively and sequentially, right? I can use the previous model in order to improve the guess of the model. Some of the most, the first AutoML system that used this idea was called Hyperband. Genetic programming is another idea for how to take one pipeline and turn it into a slightly better pipeline, okay? So you take some population of AutoML pipelines and you figure out, how good each of those are. If any of them is good enough, then you can say, great, I'll take it, I'm done, okay? Otherwise, I'm gonna take each of those pipelines and I'm going to change it just a little bit, right? Maybe I'll change the estimator, maybe I'll change the preprocessor, maybe I'll change the dimensionality reducer, or I could combine results from pipelines that already exist, right? So maybe I could take two pipelines that I know are good, and I could swap their estimators, or I could swap their preprocessors, okay? Now, once I've done this, I can evaluate and rank the resulting programs, take maybe, keep only the top 5 or top 10, and continue. Okay, all of those methods are methods for finding, one good pipeline. But a very good trick is to find a bunch of good pipelines and then average their results. So one classic way of doing this is an ensemble model using bootstrap aggregation, okay, bagging. This is what it looks like. I'm going to take my original data, and here I'm representing it as a collection of points that have different colors. I'm going to take a bootstrap sample of each of these, of this data set. So maybe so that means I'm going to sample it with replacement. Okay. So maybe one time when I do that, I get this resulting data set. Another time when I do it, I get more purples. And another time when I do it, I get more blues, okay, just randomly. For each of these bootstrap data sets, I'm going to fit a classifier on that data set, right? Maybe I'll use whatever other automated machine learning method to find a good pipeline on that data set, okay? Once I have a good pipeline on that data set, then I'm going to average them. Okay, so if I'm doing regression, maybe I'll just average the outputs. If I'm doing classification, maybe I'll take a majority vote of all of these classifiers in order to figure out the total prediction. Okay, so this is called an ensemble classifier, an ensemble method. The nice thing about it is it tends to perform better than any one method. In fact, you can perform better than any sort of one method that's in your space that you're considering. The downside is that it's not very interpretable. It's very hard to understand what the ensemble method is doing because there are just so many moving parts. And we're going to see more and more of that in these more and more complex AutoML systems. Okay. A similar idea is called stacking. So stacking takes the input to your machine learning model, so that's the features of your data, and it runs them through a bunch of different models. Okay, and you could use any of the previous techniques I've talked about in order to produce a bunch of different models or a bunch of different pipelines that you think will perform well on your input. Okay, now instead of just averaging those predictions, what we're going to do is we're going to treat the predictions of each of these models as new features for our data set. So we're going to concatenate the old features for our data set using this arrow with the predictions from each of these models, okay? And those are the new features that we are going to use to train new models, okay? So we could keep iterating this many, many times. In some ways, this looks like, it looks kind of like a deep neural net, okay? Except in this case, instead of the neurons being, simple ReLUs, here the neurons are, machine learning models or pipelines. Okay. But it's very meta. Okay, so at the final layer, I'm going to do just a simple ensemble. I'm going to take the outputs of each of these models, and I'm going to form an ensemble. I'll take the majority vote, or maybe weight them each differently depending on how they perform, and call that my output. Okay, so all of the methods that I've discussed so far are ways of learning from a single data set. Now I want to tell you about how to learn across different data sets. That's called meta-learning. Okay, so standard learning, what do? Right? You take your whole training set and you split it, right, into you take your whole data set and you split it into the test set, a validation set, and the training set. Right, you train your machine learning model on the training set. You might choose hyperparameters by looking at which model works best on the validation set, and then you evaluate the performance on the test set. Meta-learning does the same thing, but it splits learning instances. So, oftentimes what you would do is you would take a big collection of data sets. And these exist on the internet. You could take all the data sets in OpenML. You could take all the data sets on Kaggle. Right? Or maybe for your company, you have a collection of data sets that you think is interesting, right? Maybe you've got the stock market data on different days, or you've got different assets. Maybe you've got data from a bunch of different self-driving cars, and you want to consider each self-driving car to be its own data set. Maybe you've got just a bunch of science experiments that different people in your organization are doing, right? And each one of them produces its own data set, right? And you want to be able to predict better, choose a better machine learning model on a new data set that's similar to these data sets that you've seen in the past. So in this case, what you might do is you might take your set of data sets and split it into a training set of data sets, okay, which we could call meta training, a validation set of data sets, and a test set of data sets. Okay, so on the meta training set of data sets, you're going to learn a good AutoML model. You could validate the hyperparameters of your AutoML model on the meta validation set, and you can test how well your AutoML model works on the meta test data set. Okay. So let me give you some examples of some meta learning methods. These are drawn from my own work. Okay. So the first one I'm going to tell you about is called OBO. It starts with a set of M data sets and a set of N machine learning models. Okay. What we do is we measure the error of every model on every data set. Now, this obviously takes a very long time, but this is sort of a pre-processing step, right? The fast part will be later. Okay. We take the error of each model on each data set and we put that into an M by N data table that we'll call A. So there's one row for every data set and one column for every machine learning model. The entries are the cross-validated error of that model run on that data set. Okay. Now what we're going to do is we're going to use PCA in order to compute a factorization of this data set. Okay, so we're going to approximate this error matrix with a low rank matrix, x times y. So there's going to be one row of x for every data set, one column of y for every model. And each error is going to be predicted by the inner product between a row of x and a column of y. Okay. Now, a new data set comes along. This is the data set that we want to do automated machine learning on. We want to make predictions fast on this new data set. And you can see that we'd be able to choose a model on this new data set if we knew which entry in this row was the lowest, right? The entry with the lowest value in this row is the model that has the lowest error on this data set. That's what we want to know. Okay. If you look over at this factorized view, you can see that this data set can be represented by two parameters, right? Just its vector little x. Okay, if I knew its vector little x, then I would multiply by this matrix y in order to predict the error of every model on this new data set. So how do I estimate this little x? Well, I can evaluate a couple of machine learning models on this data set. And I can, so here I'm showing evaluating 3 machine learning models on this data set. I can use that to estimate this row of x using, say, least squares. Okay, so now I've got a guess for this latent factor corresponding to the data set. Now I just multiply that by y in order to make predictions for every other entry in this row. Great, so now I've got sort of imputations for these other entries. This is awesome because now I can look at which imputed entry is the lowest and say, maybe that's going to be a really good machine learning model. That's the one I'm going to recommend. Okay, so that's how the OBO system for automated machine learning works. So you can think about the rows of x as dataset metafeatures, columns of y as model metafeatures, and these entries as predicted model performance. Okay. Now, there are actually lots of other ways of getting dataset metafeatures or model metafeatures. Okay. One classic way of getting dataset metafeatures that was introduced by an AutoML system called AutoScikit-learn is to just run a bunch of really fast algorithms on your dataset. Right, so anything that runs fast enough, I'll consider just a dataset metafeature. So I'll collect the outputs of all these sort of really simple algorithms on my dataset into some vector that I call the dataset metafeatures. And I could take those dataset metafeatures and try to predict using the metafeatures which model is going to perform the best. Okay, a more complex system that builds on this idea is called RealTime AutoML. This is joint work by me, Ido Drori, and a bunch of other awesome people. And the way that this works is you take a collection of data sets and their descriptions. Okay, so someone says something about the data set, they've typed up what this data set is about. And on the data set, on the data itself, you compute a bunch of data set metafeatures. And on the description, you use a model from natural language processing, right? Maybe BERT, maybe GPT-3, maybe something even fancier that will be invented in the future. And you compute an embedding for that text description, okay? So now we've got metafeatures for the data, metafeatures for the description. We put those together, okay? That's our vector representing the data set, okay? Now we can use those vectors representing the data set in order to figure out which model will work best on the data set. What we do actually is essentially a k-nearest neighbors type approach that we do it using a graph neural network. Okay, you can do a similar trick in order to find a representation for each pipeline. So what we do is on each data set, we can actually run any existing automated machine learning method. We could run AlphaD3M, Teapot, Obo, AutoSklearn. Each of those is going to produce best pipeline. We can take the code for those pipelines and we can use, again, our natural language processing model to make a description of that code. Okay, so that's also, that goes into our representation of the data set. Okay, this is a little bit like stacking. And then essentially we use a GNN model. Think of it like k-nearest neighbors in order to predict for a new data set which method is going to work best on the new data set. Okay, so you could see that these automated machine learning ideas can get pretty complicated, pretty sophisticated. In some ways, what I like about automated machine learning is you're taking any idea that you use for machine learning, and you can put them together in really creative ways in order to make new AutoML systems that have, good performance and that use features that you might not have thought were, features that you could use to find a good machine learning model. Okay, let me tell you about a couple of existing AutoML systems and see how they work. Okay, so there's a pretty large number of them at this point. One of the earliest was AutoWeka, that does Bayesian optimization on a conditional search space. AutoSKLearn was also was developed 6 years ago. It uses Metalearning plus Bayesian optimization. Teapot is maybe the top system using genetic programming. Hyperband and Flammel are both using a multi-armed bandit approach. Flammel is pretty recent and is even faster than Hyperband. OBO uses matrix and probabilistic matrix factorization, both use matrix factorization, and they have different ways of sort of picking which methods to use in order to estimate the dataset meta features. One uses Bayesian optimization and OBO uses experiment design. AutoGluon is a sort of top-of-the-line system that comes out of Amazon that uses ensembling and stacking. And then sort of each cloud provider has essentially its own, recommended automated machine learning system. So Google has AutoML Tabular, Microsoft Azure has AutoML, and Amazon's has AutoGluon on SageMaker. H2O is another company that produces really great machine learning software, and they have their own AutoML method that's mostly using random search plus ensembling. Okay, there's a bunch of methods also for neural architecture search. I'm not going to talk too much about those methods because it's outside the scope, but there's really interesting ideas going on there, and the ideas there are actually quite different from the ideas that work best on tabular data. Okay. So let me show you, how well do these systems work? Okay, so this is a figure that comes from the AutoGluon tabular paper. Here on the left, you'll see the performance on a bunch of data sets that together make up an AutoML benchmark. The black line is the performance of AutoGluon on this data set. And you can see a bunch of other systems like AutoSKLearn, Teapot, AutoWeka, H2O, GCP tables compared to the performance of AutoGluon. So you can see AutoGluon is doing quite well across all of these data sets in comparison to these others. But on some data sets, AutoSKLearn performs better or Teapot performs better. So you can see that there's still a lot of competition. And I guess what that means is that there's something that we still haven't learned about these data sets, right? If we understood what was driving the better performance of one or these other automated machine learning methods on this data set, right, then we would know how to build a better automated machine learning method. So this is one thing that I love about AutoML is it's trying to help you discover, right, what's the structure of these data sets? How are these data sets similar or different? What ideas work best to learn from these data sets? And then you can see the performance on a bunch of data sets that are in the Kaggle benchmark. And you can see the AutoGluon is doing well sort of across the board, but there are other methods that are also doing quite well. The GCP tables in particular is doing quite well here. Okay, and just to get a sense for how long it takes, so most of these AutoML methods have as a parameter, how long do you want it to run? So here we're taking 1 hour to perform well on these problems, and here we're running it for 4 hours. Okay, that's relatively long times. Other AutoML systems are targeted more towards really short times. If you need to spend, maybe just 60 seconds to get a good prediction. So this is a picture from a paper on Flammel, which shows the performance on a bunch of different data sets. In fact, these data sets are ordered by size counterclockwise from the smallest blood transfusion to the largest Ricard. Okay, so on the smallest data set, you can see that Flammel is performing actually super well with a very short time budget. On some of these other methods are also performing well, but some are performing very poorly. Like Cloud AutoML is not doing well at all at the 60-second budget. On the other hand, if you increase the time budget, all of the methods should perform on average better as the time budget goes up, and the performances become more and more similar as the time budget increases. Okay, so even if you only had 60 seconds and not a full hour, you could still get a really good prediction using AutoML, and I bet you'd get a better prediction than using, if you went at your keyboard with just scikit-learn for 60 seconds. Okay. So we're coming towards the end of the talk. I want to tell you about some remaining challenges that I see as being pretty key for continued progress in automated machine learning. Maybe the most important challenge is interpretability. Most of these automated machine learning methods result in really complicated pipelines. Just choosing hyperparameters, maybe that's not so crazy. Once you start choosing estimators, choosing other components of the pipeline, ensembling the model, stacking the model, using meta-learning, it becomes very hard to explain why your model makes the predictions it does. Okay, so in some ways, automated machine learning is the enemy of interpretability. Okay, so on some data sets, maybe we need interpretability. On other data sets, maybe we don't. Understanding the difference is important, but it might also be interesting to develop automated machine learning systems that are targeted towards producing interpretable models. Feature engineering is another huge challenge. Okay, most of really all of the methods that I showed you, they start with some features, right? And you depending on what features you input, you could get better or worse results. And they're not going to be able to find out, about important but feature transformations that might require domain knowledge, right? They're never going to be able to learn a Fourier transform of your data, right? If that would really, really help performance. The ones that come closest are probably the ones that use some deep neural net layers or include deep neural nets among the estimators that they might select from. But even then, you're limited by the fact that you don't have that long to learn, and deep neural nets do take quite a while to train and quite a number of training examples to train. Okay, so this is a place where human ingenuity can really help. If you can really figure out what the right feature transformations are to make your problem easier to learn, or which features to collect, right? What data to go out in the world and actually acquire, that can make a huge difference in the performance of your model. Okay, so you might imagine that a better sort of like the full human in the loop method for automated machine learning has a human designing a feature set, feeding it to an automated machine learning system, which outputs something, right? And then using that result in order to figure out how to change the features in order to improve performance. Overfitting is another huge challenge. A lot of automated machine learning systems don't even think about this problem of overfitting. But if you can imagine, if you just try every machine learning model, you will find a machine learning model that overfits to your data set. And in fact, you can start to sort of overfitting to your test set because you're using it so many times, because you're testing out so many different machine learning models. So systems like OBO do try to control for like overfitting and meta overfitting. Other ones don't. And that's fine if you're not going to run for very long. If you're going to run for a long time, this is a serious problem. The final problem is cost. Okay, at the extreme upper end, for example, Google's reinforcement learning-based neural architecture search uses 1,000 GPU days to train. Okay, so over $70,000 on, say, Amazon AWS in order to train that neural architecture search model. That's clearly more than most people can budget, and whether or not that's affordable, right, depends on who's running the model. In some ways, automated machine learning makes this less of an issue, right? You can imagine training an automated machine learning method and then using that automated machine learning methods to produce really quick predictions as to the best pipeline on new data sets. And if you use it across enough new data sets, then it might be worth your while to spend that much money training the AutoML method. So just a quick summary. I've shown you a bunch of AutoML methods and a bunch of ideas from AutoML that automatically pick a good machine learning pipeline for your problem. I've shown you a bunch of easy to use packages. They've got really simple APIs. And I've tried to explain some of the most important ideas that power these systems. I'd love to take your questions and discuss more about this exciting field. Bye.